Welcome to your AP Calculus review question video. So the way this is going to work, I'm going to introduce a problem. I'll read it. At that point, you should pause, try to work through the problem as best you can, either to the finish or at least till you get stuck. At that point, unpause, watch what's going on, compare it to your work. And as soon as you find a mistake in your work, you should pause, update your work, and continue from the point of your mistake forward, seeing if you can get to the, and then go as far as you can to the finish or wherever you get stuck again. Unpause, watch a little bit more, check my work again or your work against mine until you find a mistake, at which point pause, correct your mistake, and rework the problem from that point forward, and just kind of continue that until you get to the finish. Okay? Please don't just watch me do the problems. Okay? All right. So here's the first one. So we have two sides of a triangle, have lengths 12 meters and 15 meters. The angle between them is increasing at a rate of 2 degrees per minute. How fast is the length of the third side increasing when the angle between the sides of fixed length is 60 degrees? So, when you read this, it's asking for, pause. Yeah, so pause. Try to do the problem. Okay. So at this point, you should have paused and tried to work through this. The first thing you want to notice is that it asks for like how fast is the length of the third side increasing. That should be your clue that what we're dealing with is a related rates problem. So I'm going to start by just kind of sketching a little picture. So we have like, some angle, we'll call it ABC. And we'll say that side AB is length 12, side BC is length 15, and this angle between them, we'll call that theta, is increasing at a rate of 2 degrees per minute. So that's a rate. So we have d theta dt is 2 degrees per minute. Now I'm going to recognize immediately that when doing any of these related rates problems, I probably would prefer this to be in radians. So my conversion formula to go from degrees to radians is pi over 180. So when I do that, I get pi over 90 radians per minute. Okay, so now I need an equation here that's going to relate the side AB, the side BC, this angle theta, and the length of this third side. I'm going to call that length x. So notice that this is not a right triangle. There's no reason we would need to assume that. In fact, it's not going to even, if it is a right triangle at one point, it's not going to stay that way because that angle is increasing. So what I'm going to use is a way to relate those three quantities together in a non-right triangle sense. I'm going to use the law of cosines. So I have x squared is equal to 12 squared plus 15 squared minus 2 times 12 times 15 times cosine theta. So that's my law of cosines. I can simplify that down a little bit. 12 squared plus 15 squared is going to be 369, and 2 times 12 times 15 is 360. So I have 369 minus 360 cosine theta. I'm now going to differentiate. So I have 2x dx dt equals 369 minus 360 cosine, not cosine though, derivative of cosine is sine theta, and then d theta dt. Okay. So, and it asks then, when is the angle between, or I'm sorry, how fast is that rate of the third side increasing? So we're looking for dx dt when theta is equal to 60 degrees. Again, I'm going to convert 60 degrees into radians. So when I do that, I get pi over 3. Now, I have, what do I have so far? I have d theta dt. I have theta. What I don't have yet is x. Well, how can I find x? I can use this equation to figure out what x is when theta is pi over 3. So I'm just going to type that into my calculator. And now I'm going to be a little bit careful about my mode. I'm going to use radian mode since I have everything else written as radians. So to get the x by itself, I'm going to square root both sides. And then 369 minus 360 times cosine of pi over 3. So that's my value for x. Or I suppose I could get a, oops. If I did this, I could get it without the square root on it, which I'd probably prefer. So x is going to be the square root of 189. And now I have everything I need. So dx dt is going to equal 369 minus 360 sine of pi over 3 times pi over 90 divided by square root, or 2 times the square root of 189. And that's just calculator time at that point. Alpha at 369 minus 360 sine pi over 3 times pi over 90 over 2 root 189. So I get about 1308 or 1302 meters per minute. Again, I know the unit because my side lengths were in meters and the time unit on my rate in the problem was in minutes. Okay, let's look at the next one then. Go away. This problem is 4.9, number 65. So it says a stone is dropped from the upper observation deck of the CN Tower, 450 meters above the ground. Find the distance of the stone above the ground level at time t. How long does it take the stone to reach the ground? With what velocity does it strike the ground? And then part D, if the stone is thrown downward with a speed of 5 meters per second, how long does it take to reach the ground? So, pause here and try to work this on your own. Okay, I'm going to start now. So for part A here, it says find the distance of the stone above the ground at time t. So what it's asking for is S of t. So what I'm going to do is I'm going to start with A of t, and I'm going to do antiderivatives until I get to S of t. Now, the stone is just being dropped, so the only force acting on it is gravity, which is negative 9.8 meters per second squared. And that's constant for everything on Earth, or near the Earth's surface, and we'll say 450 meters is still pretty near the Earth's surface. So the first antiderivative of acceleration is velocity. Maybe we should say v of t equals, yeah, we'll just do that. So this just becomes 9.8 t plus c. Now we have to figure out what this constant is. In the problem, we've been given enough information to tell what this constant is. And the key here is that the stone is being dropped. So what does that mean? It means the velocity at time 0 is 0. That just tells me c is 0. So v of t is negative 9.8 t. Okay. And s of t then is the antiderivative of velocity. So that's going to be negative 9.8. And then I'm going to t to the 1 plus 1 over 1 plus 1. And then I'll have plus c. Now again, we have to solve for this c. And again, the problem is telling me how to do that, because it tells me that we're dropping from 450 above the ground. So that s of 0 is 450. So I know that s of 0 is equal to negative 4.9 t squared plus c. Oops. It should be negative 4.9, 0 squared plus c is equal to 450. Or, well, let's make this a different letter. Let's just make a d for not wanting to get things confused. So d is 450. So s of t is equal to negative 4.9 t squared plus 450. So that's my answer for part A. Now part B asks, how long does it take for the stone to reach the ground? So we want to find s of t equal to 0. So this is just like an Algebra 2 problem. So to solve this quadratic, it's equal to 0. Since there's no linear term, I can just solve this directly by subtracting 450 from both sides, dividing by the negative 4.9, and then square rooting both sides. So I have the square root of, or plus or minus the square root of 450 divided by 4.9. And again, I know that in this context, that time really needs to be positive. So I can just drop that, and we'll just type this into our calculator. So I get about 9.58 seconds. And then C asks, with what velocity does it strike the ground? Well, I know how long it's going to take, 9.58 seconds to reach the ground. So I just want the velocity at that time. So I'm just going to be using my velocity equation. Oops. So negative 9.8 times 9.58. And again, we'll just plug that into our calculator. I get negative 93.91 meters per second. Oh, 93.91. And then in part D, it says if the stone is thrown downward with a speed of 5 meters per second, how long does it take to reach the ground? Well, what that tells me is that in this situation, v of 0 needs to equal 5. So I'm just going to rework the previous steps, but I'm just going to do these in blue. So start the same way. The acceleration is negative 9.8. The velocity is negative 9.8 t plus c, but to solve for c, instead of equaling 0, it's going to equal 5. And that tells me c is 5. So I have that. So when I differentiate, I have plus 5t plus d. So there I would get 5 times, oops, wanted to keep that as blue. 5 times 0 plus d is equal to 450. But again, still d is 450. No great shock there. So 5t plus 450. And then from there, we just, again, set s of t equal to 0. And now, that's a quadratic where I do have a linear term, so I'm going to use the quadratic formula. Hopefully you can look at that and say that factoring is going to be a fool's errand. Quadratic formula will be much easier there. So negative b, and I'll have plus or minus, so I'm going to check both of them. I'm going to start with the plus though. 5 squared minus 4 times a, make sure you take your negative sign, times c, divided by 2 times a. Again, got to be careful, take your negative sign. So that's a negative. So that's probably not the one we want. Again, hopefully it's pretty intuitive that the time we're looking for needs to be positive. So just update that and do the minus one. So make sure you use a subtraction symbol, not a negative sign. I get about 10.11. And there's my answer. Okay. That's good. Let's go ahead and take a look at the next one then. So it says that, I think I wanted to do 23 here. Nope. It says find the derivative of the function using the definition of a derivative, and then state the domain of the function and the domain of its derivative. Okay? So again, let's pause this, try to work through this, and then once you've gotten to a stopping point, tune back in. All right, so I'm going to start. So the definition of a derivative, the limit as h approaches 0, of f of x plus h minus f of x over h. So in our case, it's really f of t. So we'll do that. So I'm going to just plug in. So t plus h goes in for my t's, just like a function composition would. And then I got to make sure that since my what I'm subtracting is a polynomial, I'm going to put that parenthesis there so I make sure that I distribute that. And uh-oh, Mr. Kulik got sloppy, made a little mistake. That's not what I wanted. Okay, because he forgot his limit. Okay. So I'm going to go ahead and simplify things down. So I'm going to distribute the 5 through. I'm going to FOIL that out and then distribute the negative 9 through. And then distribute my negative sign through. And again, got carried away and forgot my limit. So easy to do, but at least I'm catching them, right guys? Okay. So what I'm going to do now is I'm going to combine some like terms. So I have a positive 5t and a negative 5t. I have a negative 9t squared and a positive 9t squared. Those are all canceling out, which is fantastic, because everything that's left now has a factor of h. So I can reduce an h from everything in the numerator with the h in the denominator. If that does not happen, you've likely just made an algebra mistake. So you'd want to start back over, or at least go backtracking to look for your algebra mistake. So what I'm left with is a 5 minus 18t minus 9h. And when I do my direct substitution to evaluate this limit, I can just plug in 0 for h. And notice I dropped my limit here because I evaluated it. I did my direct substitution. So there's my derivative. Notice that that's a linear function, so its domain should be all real numbers. And I guess we go back and look at our original function. That's a polynomial, so I know, again, the domain is all real numbers. And that's that. So again, the algebra is a little sticky there, but nothing we can't handle. All right, let's take a look at the next one. So this is from section 2.3, number 38. It says if 2x is less than or equal to g of x, which is less than or equal to x to the 4th minus x squared plus 2 for all x, so that inequality holds for all values of x, evaluate the limit as x approaches 1 of g of x. So our hint here is this inequality that they've given us. This reminds me very much of the squeeze theorem. So let's go back and recall what the squeeze theorem says. So the squeeze theorem states if f of x is less than or equal to g of x, which is less than or equal to h of x, when x is near a, except possibly at a, and the limit of f of x equals the limit of h of x, which is all equal to L, then the limit of g of x is equal to L. So what we have given to us is this piece, right? Because it's for all x, including specifically 1, which is like the a in this case. So to evaluate the limit as x approaches 1 of g of x, we want to see if this holds. And if it doesn't, well, then we're probably just out of luck. So we'll just do the limit as x approaches 1 of 2x. Again, I notice 2x is a continuous polynomial, so I can just use direct substitution. I get 2. And the limit as x approaches 1 of x squared, x to the 4th, minus x squared plus 2. Again, I notice this is a polynomial, so it's continuous, so I can use direct substitution. So I have 2 to the 4th minus 2 squared. What am I doing with 2's? We're supposed to be plugging 1 in. Ay, just too many 2's in there, got me all excited. So 1 to the 4th is 1, minus 1 squared, which is 1, so I just get 0 minus, or plus 2, which is 2. So I can say that the limit as x approaches 1 of 2x equals the limit as x approaches 1 of x to the 4th minus x squared plus 2, all equal to 2. So we have, by the squeeze theorem, the limit as x approaches 1 of, what was our, g of x was our name, has got to equal 2 also. And we're done. So again, this just boiled down to doing the limits of the upper and lower bound, and as long as they're the same, then whatever they're bounding also has the same limit, which is pretty nice. All right, let's take a look at the next one then. So to show that in this next one is from section 2.5, it's number 39. The directions say that show f is continuous on the interval from negative infinity to positive infinity. Okay. Well, again, pause, try to work through this. When we unpause, what I'm going to notice is, okay, I have a piecewise function, so the first part of my function, that rule goes from negative infinity to negative 1, and the second part of my piecewise function goes from 1 to positive infinity. Okay, so I notice from negative 1 to 1, f of x equals x squared is a polynomial. Therefore, we're continuous there. And then on the interval from 1 to positive infinity, notice I used the open interval here, not the closed. F of x is equal to the square root of x, which is a radical. And 1 is to positive, these are all positive numbers, which are definitely in the domain of the square root. So I know that radicals are continuous on their domain, and 1 to positive infinity is on their domain. So I know that part's continuous. The only question is what's happening at x equals 1, the boundary between the two parts. So I need to show continuity at a point. I need to show the limit as x approaches 1 from the left of f of x is equal to the limit as x approaches 1 from the right of f of x, which is equal to f of 1. Okay? So the limit as x approaches 1 from the left of f of x is the limit as x approaches 1 of x squared, which again I can just do by direct substitution, which is 1. The limit as x approaches 1 from the right of f of x is the limit as x approaches 1 of the square root of x, which again, continuous on its domain, so it's the square root of 1, which is 1. And then if I wanted to do f of 1, well, the rule says when x is greater than or equal to 1, I should do the square root of x, which is 1. So I know that we are continuous at x equal 1. So that means we are continuous from negative 1 to 1, at 1, and then from 1 to positive infinity, so we're good. Notice that these two rules here are super helpful, right? Knowing that to show continuity over that interval, I can just use that the function is continuous on that interval. So that's quite helpful. Okay, let's take a look at the next one. We're not doing all of these. I think we're just going to look at number 27 here. Okay. So again, this came from section 4.1. So it says sketch the graph of f by hand, and then use your sketch to find the absolute and local max and min values of x. Okay. So again, this is a piecewise function that I'm going to graph. So, and I look at this. The first piece is linear. So from 0 to 2, f of x is equal to 1 minus x. So I'm just going to make a little xy table, because to graph a linear function, I just need 2 points. Now the two values of x I'm going to pick should be, oops, that should be less than 2 strictly, are going to be 0 and 2. So 1 minus 0 is 1, 1 minus 2 is negative 1. And then from 2 to 3, notice that this is a closed interval. F of x is equal to 2x minus 4, another linear function. Again, to graph a linear function, I just need 2 points. The 2 points I'm going to choose, shocker of the century, is going to be the endpoints 2 and 3. So 2 times 2 minus 4 is 0. 2 times 3 minus 4 is 2. So let's go ahead and sketch ourselves a little graph. So I have, let's do a little better job than that. Okay, so we go from 0 to 2, so 1, 2, and then from 2 to 3, so 2, 3. Okay, so I have 0, 1, and then 2, negative 1, and I'm going to do an open interval there. Oops, 2, negative 1. So again, I know that needs a closed circle at 0 because it was less than or equal to, and I need an open circle at 2 because it's strictly less than 2. And then I plot my next point, so that's 2, 0, and then 3, 2. So again, those both get closed circles because I have less than or equal to on each of them. And notice that it's not going forever, so this is all I got. Okay? So this is my piecewise function. Notice that this is not continuous. And notice that the derivative is going to fail to exist at x equals 2 because of the discontinuity. But even if these were touching, the derivative would fail to exist because the slope here is negative 1 and the slope here is 2. So even if these two were connected, the derivative wouldn't exist there. So we were asked to find then the absolute and local maxes and mins. All right, so my absolute max is easy. That's 3, 2. That's the highest point on the graph anywhere. My absolute minimum does not exist. And that's because the lowest point is this open interval. So my absolute minimum is approaching negative 1, but there is no point in my function that can actually get there. And the closer and closer I get to the x value of 2, at least from the left, the closer I'm going to get to negative 1. But I can get infinitely close there. So there is no actual absolute minimum. No matter how close you want to get to 2, you can always get a little bit closer, and that'll put you a little bit smaller. So we want then our local maximums. So we have a local maximum here, because again, in that neighborhood, that's the highest point, so that would be at 0, 1. And there's no other local maximum. So my local minimum is going to be here at 2, 0. Again, in that neighborhood, that's the slowest point in that neighborhood. And that'll do it. Okay. Next one is 2.8, number 56. So this says the left-hand and right-hand derivatives of f are defined by f prime with a subscript of negative of a, being the limit as h approaches 0 from the left of my standard derivative rule, and f prime of f prime subscript plus of a is the limit from the right as h approaches 0 of my normal derivative at a point definition. So that's just kind of a little definition that's given. If these limits exist, then f prime of a exists. If and only if these one-sided derivatives exist and are equal. So it says find f prime sub negative of 4 and f prime, the left-hand derivative of 4 and the right-hand derivative of 4 for the function. And then sketch the graph of f, find out where f is discontinuous and where f is not differentiable. So another piecewise function. So I'm going to start by just doing f prime of x. Now this is a 2.8 question. I don't remember if we had our derivative shortcuts or not, but let's just pretend we do. So the derivative of 0 is 0. Derivative of 5 minus x is going to be negative 1. And the derivative of 1 over 5, x to the negative, or 1 over 5 minus x, well, that's a chain rule problem, right? I think about that as 5 minus x to the negative 1. So when I do the derivative of that, I'm going to have negative 1 minus, or times 5 minus x to the negative 2, and then times the derivative of the inside, which is going to be the derivative of 5, which is 0, minus 1, which is the derivative of negative x. So that turns into 1 over 5 minus x squared, and that's x greater than or equal to 4. So the left-hand limit then, or the left-hand derivative, is going to be the limit as x approaches 4 from the left. H approaches 0 from the left of f of 4 plus h minus f of 4 all over h. And I want to note that for approaching 4h from the left, that means that x is going to be less than 4. So I'm going to be landing in here. Or really over here. So I'm going to have limit as h approaches 0 from the left of 5 minus 4 plus h minus 5 minus 4 over h. So when I evaluate this down, I'm going to get 1 minus h minus 1 over h, and I still have that limit. Can't forget that. So when I do that, I just get -1. I don't even need to really evaluate the limit because the 1's are going to cancel out. And then the h's reduce, and we're just left with -1, and the limit of a constant is just a constant. Okay, and then we'll do the other one here. Make some space for myself. So when I do the derivative from the right, it's the same thing, but this time, if h is bigger than 0, this means x is greater than 4, so I'm going to be using that definition of f. So I'm going to have 1 over 5 minus 4 plus h minus 1 over 5 minus 4 all over h. And shoot, still have that limit in there. So when I do that, I'm going to have 1 over 1 minus h minus 5 minus 4 is 1 over 1. So this, and again, Bonehead Magoo can't remember to put a limit there first without having to erase or something. There's that. And let's go ahead and we're going to make a common denominator because right now this is in indeterminate form. You could also like L'Hopital that, I suppose, but it's going to be pretty easy to deal with. So when I do that, the negative sign is going to distribute. So I'm going to end up with just h over the limit of h over 1 minus h over h, and that's going to just reduce so we just have the limit as h approaches 0 of 1 over 1 minus h, which is positive 1. So it appears here that the derivative does not exist. So f prime of 4 does not exist. Okay. Whew. Since the left-hand and right-hand limits don't exist. Yikes. Holy shnikes, that was a lot. All right. So it says now it wants us, that was all just part A. Part B then asks us to sketch a graph of f. Well, x is less than 0 is just this, it's just f of x equals 0. So again, that's a horizontal line, so I don't really need anything for that. If you want to pick some values for, you know, for x, you just get stupid stuff like whatever. And then our next interval, so there the f of x is this linear function, 5 minus x. So again, to do that, I'm just going to do the endpoints. I'll do 0 and 4. So 5 minus 0 is 5, 5 minus 4 is 1. And then our last interval is x is greater than 4. It's going to be f of x equals 1 over 5 minus x. So here, this is a simple rational function. So I know I have a vertical asymptote at x equals 5. I have a horizontal asymptote at y equals 0. And then I need to make an xy table here. So I'm going to need do 4, 5, which is undefined because that's my asymptote, and then 6, and that should really be enough for me. So that's going to be 1 and -1. So kind of try to plot this in here now. All right, so -2, -1, and then at 0. So that's the first part of my interval, or my piecewise function. And then 0 and 5, so 1, 2, 3, 4, 5. And then 4 and 1, so 1, 2, 3, 4, and 1. Again, those are both opens. And then we have 4, 1. And then 5 is undefined. And again, we have a horizontal asymptote at y equals 0. And then 6 and -1. And probably need to have one other point here. So maybe we'll do 7, and that's going to be -1/2. So I know we're going to be doing this here. And then probably need something over here also. So maybe we do like 4.5. So that's going to be 2. So it's going to look kind of like that. So there's my function. Note that for part C, easy to see that f of x is discontinuous at x equals 0, because I have the jump discontinuity, and x equals 5, where I have the infinite discontinuity, where the asymptote is. Part D, the derivative then, again, does not exist. Well, it can't exist where f of x is undefined. So at x equals 0 and x equals 5, any discontinuities in f are going to be places where the derivative can't exist. And we have one additional place where the derivative doesn't exist, and that's here at 4, which we observed above, since the left-hand derivative isn't equal to the right-hand derivative. Like that. I think I'm going to stop here. We'll do this last one that I earmarked together on Wednesday. In fairness, it's because I did it once and then I feel like I made a mistake. So I tried it once already. And I was like, I'm making some kind of mistake, and I couldn't find it. So I want to go wait till I get back to school to be able to look at my notes. Yeah, hope that was helpful for you. And we'll see you again on Wednesday. Bye-bye.